In this video, I attempt to explain how to use an ODE solver available in Python to numerically solve the differential equations that model your simulations. We will start with a simple example. Consider the problem of a ball that is dropped from a height of 100 meters. The ball moved towards the earth under gravity, which induces an acceleration of 9.8 meters per second square in this ball. The ball also experiences a drag due to its motion through the Earth's atmosphere. The coefficient of drag is 0.01. For the sake of completeness, we assume that this ball has a mass of 100 grams. How would we simulate this system? As always, we start by writing down the differential equations that model the system. We begin by identifying the quantities of interest. We have the current position of the ball, and we also have the velocity of this ball. We will use Newton's equations of motion to model the movement of this ball through the atmosphere. This equation is known to us as F is equal to ma. We also know that this can be rewritten as a second order ODE. We will begin by reducing the second order ODE into two first order ODEs, and we know how to do that. The first equation simply denotes that velocity is the first derivative of position with respect to time, and the second equation simply captures the fact that acceleration is the first derivative of velocity with respect to time. Our next interest is to capture the forces that are acting on this ball. Now, the ball is moving under the influence of gravity, which induces an acceleration of 9.8 meters per second square. So the first force that we consider is the force due to gravity. The negative sign here simply denotes that the gravity acts in the negative y direction, or that it forces the ball to fall towards the earth. We also have the force due to drag that it experiences as it moves through the atmosphere, and we can express that using this equation here. The main quantity of interest is c, which is our coefficient of drag, and the force is always in relation to the velocity v of the ball. Furthermore, it acts against the velocity. In this case, you may notice we are also using an m here, and essentially this m will simplify the equation later on, as you will see shortly. Putting this thing together, we are able to rewrite our two first order ODEs as follows. We have the first equation remains unchanged. For the second equation, we are simply adding all the forces which are acting on the ball, and we have rewritten our second equation in this form. Now you can see why we decided to use an m here, because this equation is quite simple. It basically says that the drag experienced by the ball does not affect upon its mass. At this point, it is useful to also explicitly write the state variables. And the state variables obviously are the position of the ball and the velocity of the ball. And recall that we are dealing with a continuous system simulation, and in this particular case, the differential equations are the one that track your state variables, that express how state variables evolve over time. Now we come to the main focus of this video, where we see how we can use Python to describe the differential equations, and how we can use Python to numerically solve the simulation in question. We begin by importing numpy, and we begin by creating a variable, in this case a numpy array, to store our state. Notice that this numpy array stores two values. It stores the position and the velocity of the ball. Notice that the position is 100, and the reason we use 100 is, if you recall, we are simulating the fact that the ball is thrown at the initial height of 100 meters, is dropped at that height. Now we are going to write the function that is going to capture our differential equations. I'm calling this function f. We can use any valid Python name. The function has two required arguments. The first argument is the time, and the second argument is the state of the system. The function has a number of optional arguments which we can use to pass information that is needed to describe the differential equations. Let's begin by, let's dive into this function. What I do here is that I am extracting the position and the velocity from the state array that I've described above. Position is x, which is state 0, and velocity is v, which is state 1. I also get a g value from my arg1 and c value, which is the coefficient of drag, from arg2. The reason I have x, v, g, c here, because I want to describe these differential equations, and you notice that I need all of these quantities. I need x, v, g, and c to be able to describe these equations. I begin by writing the first differential equation, which is dx is equal to v, and this simply corresponds to the first equation. The second line, dv is equal to minus c times v, corresponds to my second equation. And this function simply returns the dx and dv quantities. It returns in the same form as the input state. It's very important. So it also returns a numpy array with the two entries. The first entry captures dx over dt, and the second entry captures dv over dt. Now I'm able to use this function and the state variable that I've defined earlier to use the ODE solver. I'm going to import the ODE solver, and I'm going to set up the ODE solver, and when I set it up, I am passing it the function that I've already defined. You may have seen this. This reminds you of the callback functions. So my ODE solver, whenever it needs to have access to the differential equations that for my simulation, it will simply call this function and get the necessary quantities. I am going to pick a particular algorithm for solving the ODE. In this case, I'm interested in RK4, so I use DOP853 as the integrator. I'm also going to set my parameters. Now, these are the optional parameters in the function f. And recall that arg1 is my g, so I set it to 9.8, and arg2 is my friction coefficient, and I set it to 0.01. Whenever my ODE solver is going to call my f, my ODE solver will not only pass the time and the state to the function f, it will also pass arg1 and arg2 values to the function. I will never call function f. At this point, the ODE solver will be calling function f as needed. I begin by setting the initial value. Initial value has two parameters. I have to set the initial state, which I've set it to be position 100, velocity 0. and initial value also sets the time, the starting time of the simulation. At this point, I'm ready to use my simulation. All I need to do, I need to select a particular time step, which is in this case 0.1, and at this point I'm able to print the state of my system. I haven't done any integration, but my system has a particular initial state. I'm able to access the state of the system by using the variable y inside the solver. So it is important to remember that solver keeps track of the state variables, and it keeps track of the state in a variable called y. So solver.y is going to print the state of the system, and solver.t here, which I guess which is hidden behind my head, is going to print the time of this system. I'm going to run my solver, and I'm going to simply say, as long as the time is less than 2, I want to integrate the solver. When you integrate the solver, you give it a particular time at which you want to solve the system. And in my case, I use the current time where the ODE solver is, and I add the time step to it, and I call the integrate function, and then I can print the state. Now, if I run this code, it will print the following output. Initially, at time 0, the state of the system is 100, position and velocity 0. At time 0.1, the position has 99.95 and the velocity is negative 0.97. Negative denotes that the ball is falling towards the earth. And you can notice as my time increases, the ball moves towards the earth, as can be seen by the fact that the height of the ball has reduced from 100 meters to 80 meters in about 2 seconds. Recall that this is the output is obtained by using the y and t variables within the solver.